So before getting into this video, I just wanted to take the opportunity to say thank you to my loyal subscribers and a welcome to all the new subscribers that have joined in recent months. The growth on this channel has been far greater than I would have ever expected when I first started making Flat Earth videos. To give you an idea, for the 2017 September equinox, I had a quiet hope to reach 2,000 subscribers by then and only just managed it a few days in advance. Now, with that milestone, I thought it would be far too optimistic to hope for 3,000 subscribers by the March 2018 equinox. However, I'm happy to report that that occurred yesterday morning, and now being Sunday the 14th of January, I'm up to 3,033 subscribers. So we've managed the 3,000 subscribers with months to spare before the equinox. So let's see what number we have by the time the equinox in March 2018 rolls around. So I have a number of projects planned in the coming months in preparation for the equinox, and in the context of the challenge which I issued to the Flat Earthers, the contest where a Mavic Pro will be the prize for anyone who can demonstrate the equinox sun angles and the operation of equatorial mounts on a flat Earth. Now, I haven't received any contest entries at this stage, but there's still 2 months to go. What I'm going to show you is that you don't actually need expensive telescopes or equatorial mounts for this challenge, or even just for the purpose of understanding how it all works. This is the little equatorial mount that I built for under $50, and I've just got a red laser attached, and as you rotate that mount on its polar axis, the red laser dot is going to move in an arc across the sky that matches the actual sun movement. And just with this simple little device, you can simulate accurately the apparent motion of the sun from any location on the Earth. There's another instrument that I've built. Now, this one cost me less than $15 with parts I bought from a craft shop yesterday. And again, this is going to help you visualize and understand the single axis of rotation, and specifically the equinox sun angles, because all we can do, we can just move based on the time of the day. This little instrument, which as I said costs $15, will allow us to predict and analyze the motion of the sun in the sky, and we can arrange that for any latitude on Earth by simply angling that board to match the latitude of our location, and that's then going to replicate the motion of the sun accurately. So taking this same concept, we're then going to analyze the equinox sun angles on a flat Earth. And I went to the printers on Friday afternoon, and I have asked them to print out a large copy of the Gleason map and also the AE map and laminate it so that I can use that for future demonstrations. And we're going to be able to see with physical models that the equinox sun angles simply don't work on a flat Earth, because this model represents the path of the sun, and we can set up a similar small scale version on this Gleason map, and you will see that the motion of the sun just does not correlate to anything logical on a flat Earth. So looking at these equinox sun angles on a globe, if that represents the apparent path of the sun that a local observer will see, you can see that matching it to the latitude means that wherever you are on the Earth, the plane of rotation is in the same direction. And that's the whole basis of how these equatorial mounts work. They're able to track the sun using a single axis of rotation. The globe is the only place the geometry works. It cannot work on a flat Earth, and I will be covering that in detail, because from different parts of the Earth, the angle of the path of the sun just does not correlate with any other location on the Earth. On the globe, it's the same angle wherever you are. We'll be covering that in a lot more detail in the future. And there are some small mirrors that I purchased also from the craft shop, again within that $15 budget. And these are to confirm that we could actually see the ISS if it was reflecting sunlight. Now, my previous experiment tested that the P900 could actually resolve the size of the image. With this one, we're going to look at it with the naked eye over a scale distance to see if reflected sunlight could be seen with a naked eye, which is what we see when the ISS flies over at night and we see the white light moving in the sky. And another aspect of what I plan to do, one thing people may not be familiar with, is that I have been heavily involved in drones for many years, even for many years before becoming involved in making flat earth videos. And one thing I like to make is very unusual drones like this one. This is a red V-tail, and also my daughter's little green goblin needed a ride, so he flies around on that thing. But these drones, they use these MEMS based flight controllers. So I have a number of experiments lined up just to demonstrate why these are actually unsuitable for any experiments into Earth's rotation. So I realised that introduction was longer than the main video will be, but just to address the topic at hand, I get asked regularly on my lighthouse videos, why can't we see the lighthouse tilting back? And I had the same question on my Ocean Monarch video from Yanchep, where I was about 45 kilometers away. Why can't we see the oil rig tilting back? Well, the problem is people are seeing images like this that are grossly exaggerating the amount of tilt that you should see over the short distance. And over the visible distance of looking at a lighthouse over 20 or 30 or even 50 kilometers, the amount of tilt is not even close to what this diagram depicts. Let's take a look at some realistic numbers of tilt. For 111 kilometers of distance across the Earth, we will only see 1 degree of tilt. Now, many of my observations of Bathurst Lighthouse are from about 20 to 25 kilometers. So we're going to see 0.18 degrees of tilt. That's less than a quarter of a degree. Even the Ocean Monarch observation from 45 kilometers will result in just 0.4 degrees. Now let's have a look at how much that is and why there is absolutely no chance that you will be able to detect that visually with a naked eye. So there's a protractor with a stick, and if I were to just tilt that stick 1 degree, it's about that much. Okay, now that's 1 degree tilted sideways. You can barely see it. Now remember, we're talking about less than half a degree, so literally just that much. But if we turn it to the angle where the tilt is actually occurring, I'm going to move that 1 degree. Can you see any difference? No, you can't. So let's take a look at a demonstration with 2 model lighthouses, and you'll see that there is just no way that you can visually detect very small angles of tilt, particularly when they are away from you. So here we have 2 lighthouses which are just garden ornaments from around the swimming pool, and I have one of them standing straight up and I have the other one tilted back an equal amount to about 220 kilometers viewing distance, so about 2 degrees. Can you tell me which one is tilted and which one is vertical? In this next demonstration, I want you to tell me if the lighthouses are tilted or if they are both vertical. They're both exactly the same. Are they tilted or vertical? And in this demonstration, they are both tilted by more than the amount of tilt we would see at 100 kilometers. What I'd like you to do is tell me how much tilt you can see. Can you see 1 degree, 2 degrees, or 5 degrees? And here's another demonstration, side by side. One of them is tilted and one of them is not. Can you see which one is tilted and by how many degrees? Have a close look. Which one is tilted and which one is straight up? See the difference? It's only a small amount, but that's about 2 degrees of tilt. That is what you would see from 200 kilometers. You're not going to notice the tilt over just 20 to 30 kilometers at all. It's impossible to detect.